Okay, so just 1 second, I bring it to the original size and let me see here. Okay, so some of you were not attending last week, and therefore just just a limited amount of information I have to bring to you. Basically, last week we didn't do anything particularly demanding. It was just an introduction to the course. And also on Thursday I taught for 1 hour only. So basically we had 3 hours, but it was an introduction. And in any case, this is my website. And on my website, the home page is like that. And basically, in the home page, you see that there is a column dedicated to teaching, and there is a link to the tutorials. And basically, in the tutorial page, which is this one, there is a link to my YouTube channel for these lectures. And in the YouTube channel, you can already see the lectures, last week's lectures, and only for Friday, because on Thursday it was just a reciprocal introduction, and on Thursday I just delivered some information on how to reach me, on how I would like to deliver this subject. And therefore, if you feel that you missed some information on how to get to me, how the subject is organized, the table of contents, just let me know for those people who did not attend last week. And basically on Friday, the lectures were, as I said, not technical. I would say that what I said on Friday is not the subject of the questions that I may ask to the exam. But in any case, if you want to have a look, these are the videos, and any lecture that will be delivered by me will be videotaped, and everything will be made available here about 1-2 days after the lecture. Basically, I'm teaching on Thursday, Friday. By the weekend, you have the lectures. And you see that each lecture is split in parts. Each part lasts about 40 minutes. So each part is about 1 hour of teaching. And because I think it's more handy if I don't join them. And also it's easier for me because the camera automatically splits the files, and if I want to get one single file I have to mount them, so it takes time. In this way it's more readily available. And also keep in mind that we will have some exercises during this subject, and tomorrow we will start. And the exercises will be developed on the personal computer. I kindly ask you to bring your own personal computer, because the room that we will use tomorrow is equipped with plugs, and therefore it's easier to use your personal computer provided you have it, instead of going to the lab, because the lab is not available by default in the hours when we teach. So basically, I think it will be enough to have a computer every 2 people. And if you don't have the opportunity to bring your laptop or to work with a friend, let me know and we will try to find a solution. So this is the first information that I deliver today. Tomorrow, please bring your PC. Keep in mind that I will videotape also the lectures when we develop exercises. This is not really super useful because it's useful to have the tapes of the lectures, but for the exercises it's not really, because it's a continuous interaction between me and you. Sometimes if you look back at the videotapes, it's not really super useful, as I said. But in the past, some students asked me to have everything videotaped, so I decided to take the switch, because at the beginning I used to take only the videos of the lectures where I was teaching the theory, but then I decided to videotape everything. This means that you have to make a selection, but you have the dates, and it's also easier to understand at the beginning of each video if it refers to an exercise or theory. So I think it's fine. And also, another thing that I said, and then I start, is that basically this tutorial page, here there is a calendar, I still have to resolve a question whether I will be able to teach on March 17, and because in principle I couldn't. And I will ask you next week if you have some time during that week, some free time, in order to not to stop for so long, because you will see here that there are, some gaps in the schedule, and I don't really like it because students forget, and also I forget sometimes. And so I will tell you if it's possible to teach the degree day or the day before, if you have some free time. I first need to check if the room is available. And another issue is you find here some supporting documents, and I said to everybody last week that this list is evolving, so I made the difference more clear between, the supporting documents that I already used, and therefore they will be available for you forever, and the supporting documents to be checked and eventually to be made available later. So I'm not sure if the supporting document below this line will be used. So please wait to download them. Okay, so basically the first supporting document that you see is a scientific paper. I just want to give you an explanation, and is an opinion paper which basically draws possible ways forward for future research in hydrology. It's quite easy to read. There is no theory there. It's just an opinion paper. Basically, this opinion paper highlights that the keyword for hydrology now, and probably in the next 10 years, will be change. And I already mentioned to you in my first lecture that I strongly believe, of course I am a co-author of the paper, so the agreement should not be a surprise to you. I fully agree with this statement. The keyword will be change, climate change, environmental change, and this change imposes a related change in the education process. And I mentioned to you then that I want this year to start a new model of teaching. Let me say, a diverse, a different model of teaching, and for this reason the documents will be updated. And my will be, after each lecture, or more or less, let's say after most of them, to write a web page of notes so that you can keep track of what I said. You have two means, the videos and the web page. And I'm not sure, because it's really time demanding to write down notes in a web page. To write down notes in general is time demanding. I'm not sure I'll be able to really do it for the whole duration, the entire duration of the subject, but I'm trying. So basically today I would like to start with the first link, and today I decided to teach by using this link, this web page. I think one problem I realize now that one limitation in doing that is that, this is my website, and the tutorial takes only the central part. I would like to try to show this frame only, but I'm not sure if I can do that. Let me just try. I don't think so. I don't think so. Okay, for the next lecture, I will see if I can find a way to better profit from the screen, because the screen is already quite small, and of course if I use only the central page, but I think you can read it. Can you confirm me that you can read here, or otherwise I can just do like that? Okay, and basically let me focus on this picture, this diagram, which I showed last week, and in order to illustrate the learning process that I would like to try with you. And basically I said we need solutions today. Civil engineering needs solutions, and our solutions refer to structures that interact with rivers, with water in general, but let me say in most cases with rivers. And we need these solutions because today we are threatened by environmental hazards, and in particular by floods and droughts. And we need solutions in order to protect society from these hazards. And keep in mind that the damages induced by floods and droughts are exponentially increasing across the world, increasing for many reasons. It's not only a matter of environmental change. It's also an increase that is driven by societal change, because if we speak about damages, damages are impacted by vulnerability. Of course, if you have an area that is not vulnerable, if a flood occurs, you have no damage. Because if a flood occurs in a desert area, you just have the flood, but nobody's living there. There are no buildings, no houses, you don't have any damage. If you have a societal change, because people go to live close to rivers, a river that is prone to floods, of course, then if you get a flood, you have a damage, because the area is vulnerable. And therefore, the societal change is making many flood-prone areas more vulnerable. And this is why the damages and the loss of lives induced by natural hazards are steadily increasing. And so basically we need solutions. We need to find ways, and this is a task of, among the others, civil engineers. We need to find ways to mitigate the hazard. And I told you that one way to mitigate these hazards is to build infrastructures. And the infrastructures, this was introduced last week, can be divided in soft and hard infrastructures. Hard infrastructures are like dams, check dams, levees. Soft infrastructures are like real-time flood forecasting systems, preparedness. Preparedness, I could define it as a soft infrastructure because you need a system to prepare people to floods. You need a system which is composed by information, education, and in some cases also policies. And therefore, preparedness is also, we can define it as a soft infrastructure. So basically I said we need solutions, so let's concentrate on them. The classic approach is reverted with respect to this scheme. Starts from the theory, the classical approach to education, and then goes through models. Models are forced by external forcings, which we quantify through data, and then we get to design variables and the solution. Now let me concentrate on the solutions, start from them, and in particular in this case, I'm skipping one step, I'm starting from the design variables. And I already mentioned to you the structures that can be designed by each of the design variables that we will consider. And then from the design variables, let's go back to models, the forcings, and then let's go back to the theory. And I made this scheme circular because we will repeat this part many times, because I will start from one selected design variable, and then I will go back to the theory, and then go back to, again, another design variables. So this scheme can easily be made circular. Also because there is, once that you get to the theory, you may have a feedback and interaction with the solutions. So there are several reasons for suggesting to make this scheme circular. Okay, so basically what we are focusing on today. Today we are focusing on the estimation of design peak flow and flood hydrograph. And these variables, design variables, can be used to design several river infrastructures. And I'm talking now of, in particular, of hard infrastructures. And here you have a series of examples. You see, you can read that the estimation, first of all, let me say that the estimation of the flood hydrograph is a key task in hydrology. And it's a task that has been applied in classical hydrology many and many times. Is a key subject of the classical subject, is a key issue in the classical subject of hydrology. So basically, I'm going back now to a classical topic that is dealt with in hydrology, and I try to deal with it with an innovative education approach. So basically, what is the reason why we need to design a flood hydrograph for it? First of all, what is an hydrograph? You have here a link to a Wikipedia page. I hope that the network is, for now it's running. So what is an hydrograph? Here there is a link to a Wikipedia page. So you just click to the link and you get the definition. But I will provide the definition to you. And you just have to listen to me. But if you wanna, make your preparation, your background deeper, you have the links to study. You don't need to look at each link and study each linked page to take my exam. Absolutely not. What you need to take my exam is just listen to me if you want to look at the videos, and I'm just asking what I'm explicitly mentioning. I will not ask you issues that are reported in the linked page. But of course, during the exam, I will realize if you took some time to look at the links, and this is positively evaluated by me. And let me be clearer, you can get the maximum score, 30, even without looking at the linked page, even without looking at additional information. Usually I use this criteria in order to give the laude. I appreciate if the students do something more. And then, if you're really interested in the subject, if you really are interested in getting, very good mark, then you may have a look at them. But my suggestion is not all of them, only the pages that look interesting to you, because you also have to follow your inspiration, because otherwise you lose too much time. There are several links. You don't need to look at all of them. And another suggestion that I would like to give to you, before looking at additional information, try to be well prepared on the required things, the required topics, because it's not a good sign if somebody realizes that you forgot about what I said during the lectures and took some time to look at the links. It's not a good idea, because what I provide to you explicitly is what I think are the basic requirements. And if you forget some of them, I suggest you to speak with me beforehand. Maybe that your decision is wise, but please speak with me, because there is a reason why I am explicitly mentioning some issues and I am linking others, because I think that these are good for additional information, but not really for building the basic knowledge. So what is an hydrograph? I already mentioned that last week, that an hydrograph is a representation of river flow along time. Usually we indicate the river flow with the symbol Q, not always, of course, you can use other symbols, but this is what we usually do in Italy and also in the international literature. So if you draw this graph, you get a representation of what is called an hydrograph. Of course, it is called an hydrograph. So usually we assume that it's a graph, but you may also represent an hydrograph with a table. So you can also draw a table, and where there is t, the independent variable, time, and then qt. And then you draw this table, and you can call even this table a hydrograph. Of course, as I said, it is called graph, and therefore we usually assume that it's a picture, but not really needed. Of course, if you have the table, it's easy to draw the picture. And basically, the hydrograph is a time series. A time series is a sequence of observations depending on time. It's quite intuitive, but keep it in mind, because in hydrology, very often we mention time series, so you need to know what is it. And again, the time series, this is not written on the notes, the time series is a sequence of observations depending on time. So as I said, the estimation of the design hydrograph is a key task in hydrology. And I consider it a key issue during this subject. And it's very challenging. So for a given river, to estimate a design flight hydrograph, namely a design variable for a given infrastructure, it's really challenging, and I will explain you why. And it is considered a professional task that requires a lot of experience. And experience means not just age, as I said. Experience means that you know what is needed, you know the models leading to the solution, and you know the theory that is needed to run these models. This is experience. Experience also depends on observation. What are the structures that we can design by using a flat hydrograph? Here you have some examples. I go back to my page, and you see here in this linked page, there is a lot of information about the hydrograph. And in particular, I will go back to this page, to this terminology specifications later. And maybe that I can turn off the slide. Just 1 second, I made an experiment. Because I'm not sure if, let me see, but no, completely dark is not a good idea. No, I think there is no way. We need to keep it. I'm sorry for that. So I will go back to these specifications later, okay? And also another thing that I mentioned last week, when you get to Wikipedia pages, I really trust Wikipedia, but I always look to these notes here, because they may highlight limitations of this particular item. In this case, the limitation is not really relevant. There is written that the page needs to be cleaned up, so no problem. I am more concerned when they say that references are needed or something like that, or that an item is controversial. So there are some items in Wikipedia which are highlighted as controversial. So in this case, you need to be a bit critical. But still, I think Wikipedia is really one of the best innovations that we had available for students in the last 10 years, because it's easily available and everything. So let me go back to my page and let's see what are the structures that can be designed with the flat hydrograph. And the structures are all structures interacting with the river, of course, because if the structure is far from the river, they are not impacted by floods. And these structures may be, and if we talk about hard structures, check dams, and here you can see, sorry for that, but sometimes I think this is a problem of the network here, because it's not connected. Let me take my USB pen, because otherwise it's going to be a pain. Yeah. Because this is an old building, the walls are very thick, and it's really a problem with the wireless. Give me 1 minute, and I will get to online with the modem. Anyway, while we wait, okay, here again. There is the problem that the signal of the cellular line is not really strong, but it works. These are check dams, and I already introduced the check dams in my last lecture. They are transversal structures that are built across a river, usually to stabilize the riverbed profile. but also in some cases they are also used, like in this case, this is what is called a selective check dam. And the selective check dam is a check dam that is permeable. You see there is not a wall here. This is a kind of a grid. And so the water can flow almost unimpacted through the check dam. What is stopped, what is blocked are the boulders. And so these structures, which need to be very heavy, they serve to the purpose of blocking what is called debris flow. It's a mix of water, boulders, and cobbles. And it's a mix that is fluid, so it flows like water. But the big difference is that the pressure that this kind of fluid, which includes stones, makes against a structure or whatever is impacted is up to 10-15 times higher than the pressure made by just water. So it's devastating. The debris flow is devastating. And for this reason, check dams, selective check dams were devised because upstream there is a storage which is kept empty because water flows through and fine sediments, they flow through, but the big boulders are blocked. But you need a very strong structure. You see that the structure is really strong. And this is why, the reason why they need to be strong is that the pressure is really relevant. As I said, up to 10-15 times the water pressure. So it's really relevant because the water pressure is already very devastating, but debris flows are really impressive. I think I have a video of a debris flow. Let me see if I can easily find it. I think it's a nice, and it's not linked to my lecture, but it's a nice, let me see, and here it is, yeah. So I think it's worth looking at it. And let me put it at full screen. So basically this is a video that was taken by a camera that was placed close to a check dam, and the camera serves to monitor the river. And after the introduction I will stop the video in order to show you the behavior of the site. First of all, here is the catchment located in north of Italy, in South Tyrol, and here. And the catchment you see is very small, 6.3 square kilometer. 6.3 means very, very small. Maybe that the main stream is something like 3 kilometers long, so it's really very small. It's something that doesn't carry any water for most of the time. But if you look at the catchment, it's a mountainous catchment which is very steep. And also you see that in the upper part of the catchment and also close to the river there is no vegetation. No vegetation means that, you know, the debris are not really cohesive. If a flood comes, they can be taken by the water and flowed downstream. And here there is the monitoring station. Basically the monitoring station, as I said, is a river gauging station. And recently the modern gauging stations are equipped with a webcam. So this is why here we have a webcam looking at the river. And so basically, let me just okay. So basically you have an idea of the dimension. This is a check dam, you see, and this is not selective. Keep in mind that in the English literature, check dams usually, the term check dam may be used to indicate what I call the selective check dam. I make a distinction between the structures that are permeable to water and those who are not. These are not permeable, and I call them check dam. And I use selective check dam for the structures that are permeable. But in the literature, you may see a different terminology. So basically, this is a check dam. And again, the purpose of this check dam is to stabilize the riverbed, the river profile, the profile of the riverbed. Why we want to stabilize it? Because as I mentioned last week, we want to stop, we want to mitigate the erosion of the riverbed. Of course, if you build a structure and this structure is durable, erosion is prevented here. And also keep in mind that one reason why we want to prevent erosion is to avoid the debris flow, because if you have a lot of debris along the riverbed and you don't have any structure fixing them, of course they can flow downstream. So look at the dimension, 8 meters, and also there is the timing, which is reported somewhere, I think up there, but basically this is in real time. So look at the speed to which this phenomenon develops. And keep in mind, you could be here, or children may be there playing close to the river. This is something that you wouldn't classify as dangerous. So let's see what happens. And it's almost no rain. You see that you don't see rain. You see some wind, but you don't see rain here. Or if it's raining, it's not really heavy. So look at the debris flow that is getting downstream, is flowing. And look at the development, it's very quick. It's a matter of some tens of seconds, no more. And this is, you understand, this is really devastating. This is not water. I'm sorry, I cannot make it available on the web because it's confidential. I got permission to show it to the students, but this is why I didn't link it to my web page. And you see, the duration of the phenomenon is about maybe 1 minute, the total duration. If you look, it's already slowing down. But still, if you think of somebody that was staying there, or some structure, or some houses close to the river, because this remained confined into the riverbed, but some of them, of course, overflow. If you have a huge flow, they can overflow. And now it's more water. You see, there are, because the flow of the sediment is concentrated at the beginning of the process, and then at the end of the event, it's basically water. Okay, so you see here some, the velocity, and this is another interesting thing. When you get a flood, I would say that if you have a big river, like the Po River, the Danube, the flood flows at about 1-2 meters per second. It's already a velocity. If you get into a river flow, into a water flow, flowing at 2 meters per second, and you get in the water up to the knees, it's difficult for you to be able to stand up. It's already a velocity, 1-2 meters, that it's really challenging. In this case, the velocity was, and this is typical of debris flow, it's much faster. It's about 6 meters per second. 6 meters per second means, in 10 seconds, in 15 seconds, it travels for 100 meters. So you don't have time to escape if it gets to you. The peak discharge, it's about 90 cubic meters per second for a catchment that was about 6 kilometers square extension. So more than 10 cubic meters per second per square kilometer. Keep in mind this order of magnitude. When you get a contribution to flood that is of the order of magnitude of 10 cubic meters per second per square kilometer of contributing area, is much, much relevant. I will explain to you in a few minutes what is a catchment and what is a contributing area, but I think you can understand me. And the duration, okay, it says here about 20 minutes, but actually the video that we saw was about a couple of minutes. And probably they included in the duration also the recessing, the slowing down of the process. And the volume was about 10,000 cubic meters. Okay, so let me go back to the check dams then. And another structure that can be designed is the levees. The levees of a river, even in this case you see a Wikipedia page, and you see an example. Levees need to be designed by using a flood hydrograph. And in the case of levees, the design variable may be the river stage instead of the river flow. The river stage is the water height. Of course, the higher the flow, the higher the height of the water. It's called the river stage. A river stage is, again, the height of water in the river, measured with respect to a reference, not necessarily the bottom of the riverbed. So you need a design hydrograph also to design levees, and also you need a design hydrograph to design dams, riverbank protections, bridges, and whatever. In some cases, we are a bit like, we don't need the definition of the full hydrograph, but it may be enough to identify the peak flow, the peak river flow. Because, of course, it's easier to identify just one number, the peak flow, instead of the whole hydrograph. And I said, in some cases, you just need the peak flow. Basically, a rule of thumb is that when you need to design infrastructure that creates storage upstream, and you have to design the storage, like for a dam, or for a retention basin, then you need the hydrograph. Every time that you need the volume of a flood as a design variable, you need the design hydrograph. If you just need the maximum of the river stage or the river flow, then of course you can limit your attention to the peak flow. For instance, usually for bridges, what you want is that the water doesn't reach the top of the bridge. So in this case, you may be just interested in the top of the water level. And for other